What if everything you thought you knew about the universe was just the beginning? What if the vast, unimaginable distances between stars weren't an insurmountable barrier, but merely a door waiting to be opened? For centuries, humanity has stared up at the night sky with a mix of wonder and longing, dreaming of what lies beyond our own cosmic neighborhood. We've sent probes to the edges of our solar system, built telescopes that peer billions of years into the past, and yet the stars still feel impossibly out of reach. But what if there was another way, a secret passage woven into the very fabric of reality itself? Picture this: a tunnel through space and time, a cosmic shortcut linking two distant points in the universe. One moment you're here on Earth, and in the blink of an eye, you could be gazing upon the crimson deserts of an alien world or floating in the glow of a nebula millions of light years away. This is the breathtaking promise of wormholes, one of the most thrilling and elusive ideas to emerge from the world of theoretical physics. Born from the mind-bending equations of Einstein's general relativity, these hypothetical bridges challenge everything we think we know about distance, time, and possibility. Today, we're embarking on a journey to explore 30 astonishing theories about wormholes and space-time travel. We'll trace their origins from the chalkboards of brilliant physicists to the farthest reaches of scientific speculation and science fiction. Along the way, we'll confront staggering paradoxes, grapple with questions about the nature of reality, and dare to ask, could these cosmic tunnels truly become humanity's gateway to the stars? Strap in, open your mind, and get ready to venture into the unknown. To truly understand the wonder of wormholes, we have to travel back in time ourselves, not through space, but to a pivotal moment in scientific history. In the year 1935, amidst a world on the brink of war, Albert Einstein and his colleague Einstein-Rosen were grappling with the profound implications of the theory of general relativity. They weren't actually searching for cosmic shortcuts. Instead, they were attempting to find a more complete description of fundamental particles like electrons, using the fabric of space-time itself. In the process of solving these incredibly complex equations, they stumbled upon something entirely unexpected: a strange, tunnel-like structure that acted as a bridge between two separate points in the universe. This was the birth of what we now call the Einstein-Rosen bridge, the very first rigorous theoretical model of a wormhole. It is crucial to clarify what they actually discovered. A wormhole isn't a hole in the traditional sense, like a pothole in a road. Think of it instead as a magnificent bridge. If you picture the universe as a vast, two-dimensional sheet of paper, a wormhole would be like a folded tube connecting a point on one side of the sheet directly to a point on the other. The journey through the tube is vastly shorter than traveling the long way across the flat surface of the paper. The openings of this tunnel are referred to as mouths, and the tunnel itself is often called the throat. What's particularly fascinating is how this idea emerged directly from the mathematics of black holes. Einstein's equations described the intense gravitational field of a black hole, a point of infinite density known as a singularity. As Einstein and Rosen explored these equations, they found that the mathematical description of a black hole's interior could be extended, creating a kind of mirror image on the other side. This led them to propose that the bridge might not just connect two distant regions of space, but could potentially connect a black hole to its theoretical opposite, a white hole. A white hole is conceived as a region of space-time where nothing can enter, but matter and energy can only pour outward. So, in this early model, an Einstein-Rosen bridge was essentially a one-way ticket from a black hole to a white hole. However, it's important to recognize that the scientists themselves viewed this discovery with a great deal of skepticism. They saw it primarily as a mathematical curiosity, an interesting artifact of their equations rather than a tangible object that could exist in the real universe. The bridge they described was incredibly unstable. The moment even a single particle of matter tried to pass through it, the tunnel would collapse catastrophically, snapping shut faster than light could travel through it. This inherent instability meant that while the bridge was a valid solution to the equations of general relativity, it didn't seem to be a practical pathway for travel. Despite this limitation, their work was revolutionary. It planted a seed demonstrating that the fabric of reality could, in theory, be threaded with these incredible shortcuts, setting the stage for decades of scientific speculation and wonder. Although Einstein and Rosen had brilliantly mapped the possibility of a bridge, their mathematical creation was more of a tantalizing mirage than a functional doorway. It posed a monumental question that would captivate a new generation of physicists. If a wormhole exists, could a person actually travel through it without being instantly obliterated? This challenge was taken up decades later by one of the most influential figures in modern theoretical physics, Kip Thorne. In the 1980s, spurred in part by conversations with his friend and renowned astronomer Carl Sagan, who was working on his novel Contact, Thorne set out to find a scientifically plausible way to make a wormhole traversable. He wasn't just looking for a mathematical oddity, he was searching for a blueprint for a machine, a set of physical laws that would allow for a safe, stable journey. The core of the problem, as Thorne and his colleagues identified, is stability. The original Einstein-Rosen bridge is catastrophically unstable, collapsing faster than the speed of light. Think of it like this: you've finally found the entrance to this cosmic tunnel, but the moment you take a single step inside, the entire passageway instantly pinches shut like a pair of scissors snapping closed on a piece of string. The immense gravitational forces within would crush anything attempting to pass through into an infinitely small point. For a wormhole to be a practical shortcut, its throat must be held open against this powerful, crushing force. The theoretical solution Thorne's work proposed is as fantastical as the wormhole itself: exotic matter. This isn't just matter from another galaxy. It's a hypothetical substance that possesses a property which defies our everyday experience: negative energy density or negative mass. If you were to push an object made of exotic matter, instead of moving away from you, it would bizarrely move toward you. This strange behavior translates into a form of repulsive gravity. While normal matter with positive mass creates attractive gravity that warps space inward, exotic matter would warp space outward. This repulsive gravity is precisely the counterforce needed to act as a cosmic support beam, propping open the fragile throat of the wormhole and preventing its immediate collapse. The challenges, however, are as immense as the concept is grand. First, we have no confirmed proof that exotic matter can exist in the stable, macroscopic quantities required. In the realm of quantum physics, certain effects, like the Casimir effect, demonstrate that negative energy densities can occur in minute amounts in a vacuum, but these are fleeting and microscopic. To stabilize a wormhole large enough for a spacecraft, you would need an astronomical amount of this exotic material, potentially equivalent to the mass energy of an entire star, woven into the very structure of the tunnel. Second, even if we could source this material, the engineering feat would be beyond our current comprehension. We would need to somehow manipulate the fundamental fabric of spacetime itself, constructing and stabilizing a structure that could withstand unbelievable forces. It's a concept that lives firmly at the boundary of known physics, a breathtaking what if that continues to drive scientific inquiry into the deepest nature of our universe. This ability to potentially manipulate time itself leads us to one of the most mind-bending implications of all. Wormholes might not just be shortcuts through space, but genuine portals to the past and future. This theory transforms a wormhole from a mere interstellar highway into a fully functional time machine, operating on principles Albert Einstein himself laid out over a century ago with his theory of special relativity. To grasp how this could work, let's construct a hypothetical scenario. Imagine we possess a stable, traversable wormhole, its two mouths sitting side by side here on Earth. Let's label them mouth A and mouth B. For now, they are perfectly synchronized. If you peer into mouth A, you see the present-day view from mouth B and vice versa. Now we decide to take mouth B on an incredible journey. We load it onto a spacecraft capable of traveling at an astonishing fraction of the speed of light, say 99.9%, and send it on a round trip to a distant star and back. Here's where Einstein's genius comes into play. Special relativity tells us that time is not absolute, it's relative to your speed. For the astronauts on that high-speed ship, time would pass much more slowly than it does for those of us who stayed behind with mouth A. This well-tested phenomenon is called time dilation. So, for the crew, the journey might only feel like a couple of years, but back on Earth, decades could have passed. When the spacecraft finally returns and we place mouth B back next to mouth A, the two mouths are no longer synchronized. They are now connected through space, but also through time. If you were to jump into mouth A on Earth in the year 2100, you might instantly emerge from mouth B not in 2100, but in the year 2080, the moment the spaceship originally returned. You've traveled 20 years into the past. Conversely, stepping into mouth B would send you 20 years into the future via mouth A. The wormhole has become a bridge not between two locations, but between two different moments in time. This creates what physicists call a closed time-like curve, a path through the cosmos that loops back onto itself, allowing for travel into one's own past. And this is where we encounter the legendary paradoxes that have fascinated philosophers and science fiction writers for generations. The most famous is the grandfather paradox. What would happen if you used this wormhole time machine to go back and prevent your own grandfather from meeting your grandmother? If you succeeded, you would never have been born, which means you could never have traveled back in time to stop the event in the first place. This creates a logical inconsistency that seems to violate the fundamental laws of cause and effect. Physicists have proposed various solutions to this puzzle. Some suggest the universe might operate under a self-consistency principle, where any actions you take in the past were always a part of history, meaning you would inevitably fail in your attempt to change a major event. Others point to the many worlds interpretation of quantum mechanics, where your actions would simply create a new, branching timeline, leaving your original history intact. These aren't just playful thought experiments, they are serious investigations into the fundamental nature of reality, forced upon us by the staggering possibility that wormholes could make time travel a theoretical inevitability. While we've been picturing wormholes as cosmic-scale superhighways, there's an entire universe of possibility hiding in the subatomic world, a realm so small it defies our everyday intuition. To find it, we must zoom in past atoms, past protons and electrons, down to the very limits of what we can meaningfully measure. At this incomprehensibly tiny scale, known as the Planck length, a distance of just 1/10,000,000th of a trillionth of a centimeter, our classical view of a smooth, serene universe completely shatters. Here, the vacuum of space is not empty and placid. Instead, it is a seething, turbulent ocean of raw potential, a state physicists poetically call quantum foam. The brilliant theoretical physicist John Wheeler, who actually coined the term wormhole in the 1950s, was a pioneer in visualizing this chaotic underpinning of reality. He proposed that the fabric of spacetime itself is not a fixed stage. At this ultimate scale, energy fluctuations are so violent that they momentarily warp the geometry of space and time. Particles and antiparticles flicker into and out of existence, borrowing energy from the vacuum before annihilating each other to pay back the debt. And woven into this frenetic dance, Wheeler suggested, could be an untold number of tiny, spontaneous wormholes. These wouldn't be the stable, spacecraft-sized tunnels of science fiction. They would be ephemeral structures bubbling up from the foam for a fleeting fraction of a second, connecting two random points in spacetime before instantly collapsing back into the chaos. The existence of this quantum foam is not just wild speculation. It is a fundamental prediction that arises when we try to marry Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small. This quest for a theory of quantum gravity is perhaps the single greatest challenge in all of modern physics. In this framework, spacetime itself must have a quantum structure, and the foam, with its wormholes and fluctuations, is the hypothesized manifestation of that structure. It suggests that the universe is fundamentally pixelated, and what we perceive as smooth, continuous space is actually the averaged outcome of an unimaginably turbulent microscopic reality. This leads to a staggering implication. The connectivity of the entire universe might be far more intricate than we ever imagined. If space is constantly frothing with these micro-wormholes, then every point in the cosmos could, for the briefest of moments, be directly linked to every other point. The void between stars, the gap between your hand and the screen you're watching, all of it could be teeming with these instantaneous subatomic shortcuts. Of course, harnessing one for travel is a fantasy with our current understanding. They are simply too small, too unstable, and too short-lived, but their theoretical existence reshapes our concept of the cosmos, suggesting that the potential for connection is woven into the very fabric of existence, waiting just beneath the surface of our perception. But if exotic matter with its bizarre negative energy is the key to holding a wormhole open, does such a thing even exist outside of theory? Remarkably, there is a well-known phenomenon in quantum physics that offers a tiny, tantalizing glimpse of this exact effect happening in a lab. It's called the Casimir effect, named after the Dutch physicist Hendrik Casimir, who first predicted it in 1948. The experiment itself is elegantly simple. Imagine taking two perfectly smooth, uncharged metal plates and placing them excruciatingly close together in a perfect vacuum. We're talking a separation of mere nanometers, a distance comparable to the size of a single molecule. According to our classical understanding of physics, in a true vacuum, nothing should happen. There should be no force between them, but the quantum world is anything but classical. Quantum field theory tells us that what we perceive as empty space is actually a seething, bubbling sea of activity. So-called virtual particles, pairs of particles and antiparticles, constantly flicker into and out of existence, borrowing energy from the vacuum for an impossibly brief moment before annihilating each other and vanishing. This endless dance happens everywhere all the time. However, when you insert those two metal plates, you change the rules of the dance on the quantum stage. The plates act like walls, restricting the kinds of quantum fluctuations that can occur in the narrow gap between them. Only certain wavelengths of these virtual particles can fit between the plates, while a full spectrum of wavelengths can exist outside them. This creates a pressure imbalance. The relentless activity of virtual particles outside the plates exerts a greater pressure than the more limited activity happening between them. The net result is that the two plates are pushed together by the vacuum of space itself. This isn't a theoretical idea, it's a measured, reproducible force. Scientists have observed this tiny but definite attractive pull between the plates, confirming Casimir's prediction. So, what does this have to do with the fantastical concept of exotic matter? The energy density in that narrow gap between the plates, calculated from the equations describing this effect, drops below zero. For that fleeting moment in that microscopic space, the vacuum exhibits a negative energy density. This is precisely the same type of repulsive gravitational effect that theorists like Kip Thorne propose is necessary to prop open a wormhole's throat. The Casimir effect, in a very real sense, is a proof of concept. It demonstrates that the laws of quantum mechanics do allow for the conditions we would need to create stable, traversable wormholes. Of course, the scale is almost laughably different. The negative energy generated in a Casimir experiment is incredibly small and fleeting. To stabilize a wormhole large enough for even a single atom to pass through, let alone a spaceship, we would need to find a way to generate a colossal amount of this negative energy density, a feat that remains firmly in the realm of speculative physics. But the mere existence of the Casimir effect is profoundly important. It tells us that the ingredient we're looking for isn't purely magical. It's written into the fundamental code of our universe, waiting for us to learn how to harness it. Yet as we reach for the stars, we are confronted by a force that seems to be pulling the universe apart on the grandest scale imaginable. This brings us to a theory that connects the intimate physics of wormholes to the single greatest mystery in all of modern cosmology: dark energy. Observations of distant supernova have revealed that the expansion of the universe isn't slowing down due to gravity, as we once thought. Instead, it's accelerating, as if some invisible, repulsive force is stretching the very fabric of spacetime itself. This mysterious driver, dubbed dark energy, constitutes about 68% of the total mass energy of the universe, yet we have almost no idea what it actually is. We can measure its effect, a powerful negative pressure that pushes galaxies away from each other, but its fundamental nature remains completely unknown. This description, a force with strong negative pressure, sounds hauntingly familiar. It echoes the very property we've been discussing as the key to stabilizing a wormhole: the repulsive gravity of exotic matter. This striking similarity has led some bold theorists to propose a breathtaking, albeit highly speculative, connection. Could dark energy and the exotic matter needed for wormholes be two manifestations of the same underlying phenomenon? Is the same cosmic repulsion that is driving the entire universe apart also the very thing that could, in theory, be used to prop open a microscopic tunnel through it? The allure of this idea is undeniable. It suggests a beautiful symmetry, a single explanation for two of physics' most profound puzzles. Perhaps the exotic matter we've been desperately searching for isn't some rare, alien substance, but is all around us, woven into the vacuum of space itself. In this scenario, the dark energy permeating the cosmos could be tapped or concentrated, its repulsive power harnessed to counteract the crushing gravity within a wormhole's throat, acting as the ultimate support structure. However, the challenges in bridging this conceptual gap are truly astronomical, spanning an almost inconceivable range of scale. Dark energy operates on the largest canvas possible, its effects only becoming noticeable across distances of millions of light years. Its influence is subtle and cumulative, gently pushing the universe apart over billions of years. The physics of wormholes, particularly traversable ones, operates at the other extreme. Stabilizing a wormhole would require an intense, localized concentration of this repulsive force, a tightly focused application of negative energy right at the wormhole's throat. We are comparing the gentle, persistent push of a continent-wide breeze to the focused, violent blast of a hurricane's eye. Translating a diffuse cosmic force into a powerful, microscopic effect is a problem we currently have no idea how to solve. Furthermore, our understanding of dark energy is still in its infancy. We don't know if it is a constant force, a field that evolves over time, or something even more strange. Without a definitive theory for what dark energy actually is, we cannot begin to speculate on how it could be manipulated, concentrated, or controlled. This theory remains a compelling what-if, a fascinating thread connecting two deep mysteries. It highlights a profound truth about our quest to understand the universe. The answers to our biggest questions are often hidden in plain sight, waiting for us to see the connections between the infinitely large and the infinitesimally small. While the idea of harnessing dark energy feels like a leap across cosmic scales, our journey through wormhole theory often brings us back to the most fundamental mathematical descriptions of our universe. To truly appreciate the elegance and the severe constraints of these cosmic structures, we must revisit the very first solution to Einstein's field equations, discovered by Carl Schwarzschild in 1916. While serving on the Russian front during World War I, Schwarzschild derived a solution describing the gravitational field outside a spherical, non-rotating mass, a description that perfectly fits a specific type of black hole. Buried within this complex mathematics was a stunning geometric revelation. The Schwarzschild solution doesn't just describe a single point of infinite density. It actually describes two separate, distinct universes connected by a bridge. This is the Schwarzschild wormhole, sometimes called an Einstein-Rosen bridge, and it represents the purest, simplest form of a wormhole in general relativity. To visualize this, imagine the classic representation of a black hole's gravity well as a funnel-shaped dip in a rubber sheet. Schwarzschild's mathematics showed that this funnel doesn't just plunge down into a bottomless pit. Instead, it curves downward, reaches a narrowest point, what we call the throat, and then curves back upward again into a mirror image funnel leading out into a completely separate region of spacetime. It's as if our universe and another one are represented by two different sheets of paper, and the Schwarzschild wormhole is a pencil stabbed through both, connecting them. One mouth of the wormhole is in our universe, the other is in that parallel universe. However, this beautiful geometric possibility is plagued by physical impossibilities that make it utterly useless for travel. The first and most critical limitation is its instability. The Schwarzschild wormhole is not a permanent tunnel, it is an ephemeral event. The moment it forms, the throat undergoes what physicists call a pinch-off. It collapses instantaneously, snapping shut faster than any signal, let alone a physical object could possibly traverse it. If you were somehow present at the moment of its creation, you would witness the bridge forming and then immediately disconnecting, leaving the two universes completely isolated from one another once more. The second, equally daunting barrier is its location. This wormhole isn't just floating in space, waiting to be discovered. Its only entrance is hidden deep within the most forbidding region in the cosmos, the event horizon of a Schwarzschild black hole. The event horizon is the point of no return, the boundary where the gravitational pull becomes so intense that not even light can escape. To even attempt to reach the wormhole throat, you would have to cross this horizon and be irrevocably pulled toward the central singularity, the point of infinite density that would crush any matter into oblivion. The wormhole itself exists behind this ultimate cosmic barrier, making it completely inaccessible and unobservable to anyone outside the black hole. So why do physicists hold this seemingly useless mathematical object in such high regard? Its importance is not practical but profound. The Schwarzschild wormhole is a crucial key to understanding the topology of the universe as described by Einstein's equations. It revealed that the solutions to these equations could describe space-time geometries that are far more complex and interconnected than anyone had previously imagined. It showed that the fabric of reality could, in theory, be woven together in ways that connect separate worlds, opening up entirely new fields of inquiry into the possible shapes and structures of the cosmos. It stands as a pristine, geometric ideal, a reminder that sometimes the most beautiful ideas in physics are those that illuminate the rules of reality, rather than offering a path to break them. Yet if the static, simplistic Schwarzschild model offers only a dead end, where else can we look for a viable path? The answer may lie in a far more dynamic and complex cosmic object, one that spins. This brings us to a significantly more promising theoretical model, the Kerr-Newman wormhole. While the Schwarzschild solution describes a black hole that is simple, static, and uncharged, most objects in our universe are not so basic. Stars, planets, and galaxies all rotate. It stands to reason that the black holes formed from collapsing stars would also possess this spin, along with an electrical charge. In 1963, physicist Roy Kerr found a solution to Einstein's field equations for a rotating black hole, which was later expanded by Ezra Newman to include an electric charge. This Kerr-Newman solution doesn't just tweak the Schwarzschild model, it completely revolutionizes the geometry of the interior, opening up a breathtaking new possibility. Within the Kerr-Newman geometry, the crushing, point-like singularity of the Schwarzschild black hole is transformed. Instead of a single, inescapable point of infinite density, the rotation smears the singularity out into a ring. Picture a diamond being compressed not into a dot but into a brilliant circular loop. This ring singularity is not just a different shape, it behaves in a radically different way. The mathematics suggest that the immense centrifugal forces generated by the rapid rotation could, in theory, counteract the gravitational collapse at the very center, potentially preventing the formation of an all-consuming singularity altogether. This has a profound implication for a would-be traveler. In the Schwarzschild model, any path leads directly into the singularity and certain destruction. But with a ring singularity, there might be a path, a trajectory through the very center of the ring that avoids the region of infinite density entirely. It's like threading the needle's eye, a narrow but possible route through the chaos. This possibility leads to an even more staggering concept, a naked wormhole. In a standard black hole, the event horizon acts as a one-way cloak, hiding the central singularity from the outside universe. However, the Kerr-Newman solution suggests that if a black hole rotates fast enough or carries a sufficient charge, the event horizon could theoretically vanish. Without this veil, the ring singularity would be exposed or naked to the rest of the universe. If this ring does indeed act as a gateway, a naked singularity would mean the wormhole throat is no longer hidden behind a point of no return. It would be out in the open, a visible and potentially accessible portal in space. You could, in theory, approach it, study it, and perhaps even enter it without first having to cross an event horizon and surrender all possibility of return. The journey through might also be far less violent than in other models. Some calculations suggest the tidal forces, the difference in gravity between your head and your feet, could be manageable, offering a smooth passage rather than a destructive spaghetti-fying pull. However, the existence of such a convenient cosmic backdoor is fiercely contested by a foundational idea in theoretical physics known as the cosmic censorship hypothesis. Proposed by physicist Roger Penrose, this hypothesis is essentially a claim about nature's inherent sense of modesty. It argues that the laws of physics abhor a naked singularity. Any such gravitational anomaly, the hypothesis states, must always be shrouded by an event horizon, forever hidden from our view. This isn't just an aesthetic preference, it's about preserving the predictable, causal nature of our universe. A naked singularity would represent a breakdown in the known laws of physics, a point where gravity becomes infinite and calculations become impossible, and its exposure could lead to unpredictable and paradoxical phenomena. If the cosmic censorship hypothesis holds true, then nature itself has vetoed the existence of easily accessible Kerr-Newman wormholes. They would be inevitably cloaked, their entrances locked away behind impassable event horizons, restoring a measure of cosmic order but slamming shut a tantalizing doorway to the stars. The debate continues, making these spinning, charged wormholes one of the most exciting and contentious frontiers in gravitational physics. Yet as we consider the mind-boggling energies required to manipulate spinning singularities, we must confront an even more exotic and primordial ingredient that theorists have proposed for building wormholes. Imagine not a collapsed star, but a relic from the very birth of the cosmos itself, a fossilized crack in the fabric of reality. This brings us to the deeply speculative but fascinating theory that wormholes could be created or sustained by entities known as cosmic strings. These aren't the strings of string theory, they are something else entirely. Theorized to have formed during the universe's earliest, most violent moments of phase transition. Much like cracks freezing into ice, cosmic strings are hypothetical one-dimensional defects in spacetime. Picture an object of almost unimaginable density, a strand that might stretch across light years of space, yet is no wider than a single proton. They are not made of any ordinary matter. They are pure space-time topology, infinitely thin lines of concentrated energy left over from the Big Bang. The gravitational influence of such an object would be as bizarre as its form. Because a cosmic string is a flaw in the very geometry of the universe, it warps the space around it in a unique way. Its immense density creates a gravitational field that is not like a planet's spherical pull, but a sharp, angular distortion. Space around a straight cosmic string would be literally puckered. If you were to travel in a perfect circle around one, you would find that your journey covers less than 360 degrees. The geometry is conical, like the surface of a pencil that has been sharpened to an infinitely fine point. This extreme warping is the key to their potential for wormhole creation. The most compelling proposal comes from physicist J. Richard Gott. He demonstrated that the incredible mass and tension of two cosmic strings moving past each other at a significant fraction of the speed of light could twist spacetime so severely that they create a closed time-like curve, a path that loops back onto itself in time, the fundamental requirement for a time machine. In this scenario, the gravitational fields of the two rapidly moving strings would essentially plate the fabric of spacetime into a knot, opening a temporary gateway. An even more direct approach suggests that a single loop of cosmic string, under the right conditions of tension and energy, could itself form the boundary of a wormhole mouth, its unimaginable mass holding the throat open against collapse. The sheer scale of energy and precision required for such an endeavor places it firmly among the most far-fetched ideas in theoretical physics. First, we have no confirmed evidence that cosmic strings even exist. They remain a beautiful mathematical prediction. Second, harnessing them would require technology of godlike power. We would need to somehow locate two of these ultra-rare filaments, accelerate them to near-light speeds on perfect trajectories, and control their passage with impossible accuracy. It's not engineering, it's cosmic-scale sculpting, using the entire universe as a workshop. The theory stands as a testament to the creativity of physicists, showing that the equations of general relativity permit pathways we are only beginning to dream of, even if building them would require us to become masters of the cosmos itself. Just when you think the universe couldn't possibly get any stranger, it reveals a connection so profound it could rewrite our understanding of reality itself. We've been exploring wormholes as cosmic tunnels and time machines, but what if their most fundamental role is far smaller and more intimate? This brings us to one of the most revolutionary and mind-bending ideas in modern theoretical physics, a conjecture that ties together the two greatest pillars of 20th century science, general relativity and quantum mechanics. It's called the ER=EPR conjecture, proposed by physicists Juan Maldaisner and Leonard Susskind. This isn't just another theory, it's a potential Rosetta Stone for decoding the deep structure of the universe. To grasp the sheer brilliance of this idea, we need to unpack its two halves. First, ER. This stands for Einstein-Rosen, the bridge-like wormhole we discussed earlier, a geometric connection through spacetime. The second half, EPR, stands for Einstein-Podolsky-Rosen, named for a famous 1935 paper that highlighted a bizarre quantum phenomenon so unsettling that Einstein himself called it spooky action at a distance. This phenomenon is what we now know as quantum entanglement. When two particles become entangled, their properties are linked in such a way that measuring the state of one particle instantly determines the state of the other, no matter how far apart they are, whether they're across a lab or on opposite sides of the galaxy. This instantaneous connection seems to violate the cosmic speed limit set by the speed of light, and it deeply troubled Einstein because it suggested information was traveling faster than light. The ER=EPR conjecture makes a staggering claim. These two ideas, one about gravity and geometry and the other about quantum weirdness, are not just analogous. They are literally the same thing. It proposes that two entangled particles are not mysteriously communicating faster than light. Instead, they are directly connected by a microscopic wormhole. That spooky action isn't a signal flying through space. It's a geometric shortcut through the fabric of spacetime itself. In this view, every time we create a pair of entangled particles, we are, in effect, creating a tiny, Planck-length scale Einstein-Rosen bridge between them. This radical idea offers an elegant solution to one of the most stubborn problems in physics, the black hole information paradox. As we mentioned earlier, Stephen Hawking showed that black holes slowly evaporate through radiation. But this Hawking radiation appears to be random, containing no information about the matter that fell in. This suggests that information is permanently destroyed, which violates a core tenet of quantum mechanics. That information must always be preserved. The paradox has plagued physicists for decades. ER equals EPR provides a beautiful way out. Imagine two entangled particles. One falls into a black hole while its partner remains outside. According to the conjecture, they are connected by a microscopic wormhole. As the black hole evaporates, the information about the infalling particle isn't lost. It's not even inside the black hole. It is transferred through this wormhole thread to its entangled partner outside, preserved perfectly in the correlations between the Hawking radiation particles. The wormhole acts as a secret channel, ensuring that information always escapes, thus upholding the laws of quantum mechanics. If this conjecture is true, its implications are earth-shattering. It suggests that the fabric of spacetime, the stage upon which the universe plays out, is not fundamental. Instead, it might emerge from something deeper, a vast cosmic web of quantum entanglement. Every connection between particles, every quantum link, could be weaving the very geometry of space and time. The smooth continuum we experience would be the result of an unimaginably complex network of microscopic wormholes, each representing an entangled pair. This would mean that without quantum entanglement, space itself would not hold together. It's a vision of the universe where the threads of quantum information are the true foundation, and the spacetime we move through is the tapestry they create. But if the universe is indeed a tapestry woven from threads of entanglement, then who or what is the weaver? This question leads us to one of the most radical and profound ideas in all of modern physics, a concept that redefines the very nature of reality, the holographic principle. To understand it, let's start with an everyday object, a credit card. On its surface is a small, shiny holographic sticker. When you tilt it, you see a three-dimensional image, perhaps a bird that seems to fly. But that entire 3D image isn't actually inside the sticker. It is encoded on the flat, two-dimensional surface of the foil. The 3D reality is a projection, an illusion generated from information stored on a lower dimensional boundary. The holographic principle applies this same stunning logic to our universe. It proposes that all the information needed to describe everything within a volume of space, every star, every planet, every person, every event happening in 3 dimensions, is actually encoded on the two-dimensional surface that bounds that volume. Think about that for a moment. The vivid, rich, 3-dimensional world you experience, the depth and the distance, might be a projection. Your entire life, your memories, the room you're in, could be nothing more than information painted on the distant, spherical boundary of the observable universe. This isn't just a metaphor, it's a serious theoretical framework that emerges from the study of black holes. Stephen Hawking's work showed that the maximum amount of information a black hole can contain is not proportional to its volume, but to the surface area of its event horizon. The holographic principle extends this astonishing rule to the entire cosmos. So, how do wormholes fit into this mind-bending picture? If our 3D reality is just a projection from a 2D surface, then the connections we perceive within that volume, the fact that you can reach out and touch an object, or that light travels from a star to your eye, must also be projections. The holographic principle suggests that what we experience as a continuous, smooth space is actually built from a network of quantum information on the boundary. And the fundamental ingredient that creates the illusion of connectivity across space is entanglement. This is where wormholes, or more precisely, their microscopic counterparts, become absolutely essential. According to the ER=EPR conjecture, every entangled connection is a tiny wormhole. In the holographic view, these countless microscopic wormholes are the threads that stitch together the pixels of the hologram. They are the mechanism that allows information stored in one location on the boundary to interact with information stored in another location, creating the seamless, interconnected 3D world we perceive. Imagine the boundary of the universe as a vast, complex computer screen with an astronomical number of pixels. Each pixel is entangled with many others. The pattern of these entanglements, this web of wormhole connections, defines the geometry of the space that is projected. A region where the pixels are highly entangled would project an area of space that is tightly connected, where objects are close together. A region with fewer entanglements would project a vast, empty void. A wormhole large enough to walk through, in this view, would simply be an enormous concentration of entanglement between two distant points on the boundary, creating a shortcut in the projected 3D image. The holographic principle doesn't just include wormholes, it demands them. They are the fundamental fabric of spacetime itself, the geometric manifestation of quantum information sharing. This framework offers a breathtakingly elegant, albeit wildly counterintuitive, vision of reality. It proposes that gravity and the very dimensions of space are not fundamental forces or stages, but emergent phenomena. They arise from the complex interactions of quantum bits of information living on a distant surface, connected by a cosmic web of wormholes. We are not living in a universe of things, but in a universe of information, a cosmic hologram, whose depth and dynamism are generated by the timeless, spooky links between its most basic parts. But if we are to turn this fleeting theoretical possibility into a practical blueprint, we need more than just a concept, we need an engineer's handbook. This is precisely what emerged from the collaboration between physicists Michael Morris and Kip Thorne in 1988. Their seminal paper didn't just describe a wormhole, it provided a detailed mathematical recipe for building a stable, traversable one. They moved the discussion beyond the one-way, collapsing tunnels of Schwarzschild and the spinning rings of Kerr, and into the realm of a true interstellar transportation system. The Morris-Thorne wormhole became the gold standard, the foundational model that directly inspired a huge wave of science fiction and serious scientific inquiry. The design specifications they outlined are both elegant and incredibly demanding. First and foremost, the geometry must be just right. A traversable wormhole must have a throat that connects two distinct, asymptotically flat regions of spacetime. This is a technical term meaning that far away from the wormhole's influence on either end, space returns to being the calm, flat, predictable void described by Einstein's special relativity. You wouldn't want to emerge from your journey into a region of warped space or intense gravity. You need a smooth landing zone. Furthermore, the throat itself cannot be a simple cylinder. It must have a shape that flares out, much like the bell of a trumpet. This flaring is crucial because it ensures that the path through the wormhole is not just a tunnel, but a stable gateway that opens into a wider universe on the other side. The most critical part of the blueprint, however, concerns the exotic material. Morris and Thorne calculated that for the wormhole to remain open and stable, this exotic matter with its negative energy density must be confined to an incredibly thin shell precisely lining the throat of the wormhole. It's not scattered throughout the structure, it is applied with the exactness of a master craftsman, creating a reinforcing layer that actively pushes against the gravitational urge to collapse. This requirement turns the construction of a wormhole from a mere feat of energy gathering into a staggering problem of ultra-precise material science and placement. Finally, and this is vital for any hope of a round trip, a Morris-Thorne wormhole must be completely free of event horizons. An event horizon is a point of no return, a one-way door. For a wormhole to be a useful tool for exploration and travel, it must allow for two-way passage. You need to be able to go to that alien star system and then come back home to tell everyone about it. The absence of an event horizon is what transforms a cosmic curiosity into a potential transportation network. The impact of this paper cannot be overstated. It was a paradigm shift. Before Morris and Thorne, wormholes were largely seen as mathematical ghosts, interesting solutions to equations that had no bearing on reality. Their work changed the conversation. It provided a concrete set of criteria that physicists could actually work with, analyze, and try to find loopholes for. It asked the question, how, instead of just if, and in doing so, it gave generations of scientists and dreamers a tangible goal to reach for, a detailed map for a journey to the farthest shores of the cosmos. Yet every bridge must have two ends, and if one side of the Einstein-Rosen bridge plunges into the inescapable darkness of a black hole, what awaits on the opposite shore? The mathematics of general relativity presents us with a truly bizarre counterpart, the white hole. If a black hole is a cosmic one-way street where gravity is so intense that nothing, not even light, can escape its pull, a white hole is its exact theoretical opposite in time. It is a region of space-time where nothing can enter, a cosmic gusher from which matter and energy can only explosively pour outward. Imagine trying to swim against the current of the most powerful waterfall in the universe. No matter how hard you fought, you would be violently ejected. That is the nature of a white hole, a region of pure, relentless expulsion. In the original Einstein-Rosen model, this was the complete picture. The wormhole was never envisioned as a tunnel between 2 points in our own universe. Instead, it was a bridge connecting two different realities, a black hole in our cosmos to a white hole in another. One mouth acts as an ultimate sink, drawing everything in. The other acts as an ultimate source, spewing everything out. This creates a beautiful, symmetric vision of cosmic plumbing, where matter falls in here and is ejected somewhere else entirely. However, most physicists today view white holes as mathematical phantoms rather than physical objects we might one day observe. The primary reason is a fundamental law of nature, the second law of thermodynamics. This law states that entropy, a measure of disorder, always increases in a closed system like our universe. White holes seem to violate this principle spectacularly. A white hole would be a region of incredibly low entropy, a perfectly ordered eruption of energy that never becomes more disordered. It would be like a glass of water spontaneously unmixing itself into neat layers of hot and cold. Nature simply doesn't work that way. Disorder always wins. Furthermore, white holes are considered catastrophically unstable. The moment any external matter, even a single hydrogen atom floating in the void, attempted to cross its boundary, the entire structure would collapse. The equations suggest it would immediately transform into a black hole, snapping the wormhole connection shut and sealing the doorway forever. This fragility makes the long-term existence of a white hole in our universe seem practically impossible. Despite these formidable objections, the idea is so compelling that scientists have speculated about where one might look for such an object. One dramatic hypothesis suggests that the Big Bang itself could have been the ultimate white hole event, a singular eruption of all matter and energy from a point of infinite density. Another more recent idea proposes that certain high-energy astrophysical events, like the mysterious gamma-ray bursts we detect from across the cosmos, could be the death throes of a white hole. Yet, upon closer inspection, these theories don't hold up. The Big Bang was the expansion of space itself, not an explosion within space, and gamma-ray bursts have much more convincing explanations, such as the collapse of massive stars or the collisions of neutron stars. To date, there is not a single piece of observational evidence that points to the existence of a white hole. They remain a fascinating what-if locked within the equations of general relativity, a beautiful idea that the universe, in its relentless march toward disorder, appears to have rejected. While we grapple with the immense energies needed to build wormholes, what if the answer to one of cosmology's greatest puzzles has been hiding in plain sight, woven into the very fabric of our galaxy? This brings us to a truly unconventional and fascinating proposal, that wormholes themselves could be the elusive dark matter that astronomers have been searching for. For decades, we've known that something is wrong with our inventory of the universe. When we observe the way galaxies spin, the stars on the outer edges are moving far too quickly. According to the laws of gravity and the amount of visible matter we can see, stars, gas, and dust, these outer stars should be flung off into the void. The fact that they aren't means something invisible with immense gravity is holding them in place. We call this something dark matter, and it makes up about 27% of the universe, yet we have no idea what it actually is. The leading theory posits that dark matter is a sea of exotic, undiscovered particles that barely interact with light or normal matter, only making their presence known through their gravitational pull. But some physicists have proposed a radically different idea. What if dark matter isn't made of particles at all? What if it is made of things, specifically a vast number of primordial wormholes? The theory suggests that in the unimaginable chaos of the Big Bang, countless microscopic wormholes could have been spontaneously created, frozen into the fabric of the newborn universe like bubbles in ice. These wouldn't be the carefully constructed Morris Thorne tunnels. They would be natural, simple structures, relics of the universe's first moments. Over billions of years, as matter clumped together to form galaxies, these ancient wormholes would have been gravitationally drawn into the mix, clustering in the vast halos that surround galaxies like ours. Because they are objects with mass, they would exert a gravitational pull. A sufficient number of them, scattered throughout a galaxy, could provide the extra gravitational glue needed to explain the rotation curves of stars. In this scenario, we wouldn't need to invent a new, invisible particle. The missing mass would be accounted for by a cosmic population of tiny, massive objects we already know are permitted by Einstein's equations. However, this elegant idea faces several monumental challenges that have prevented it from becoming a mainstream theory. The first and most pressing issue is stability. How would these primordial wormholes survive for 13.8 billion years without collapsing? As we've discussed, wormholes are notoriously unstable without exotic matter to hold them open. The theory relies on these wormholes being simple, Schwarzschild-like structures which are inherently unstable and prone to immediate collapse. Proponents suggest that some unknown quantum gravitational effect in the early universe might have stabilized them, but this is purely speculative. Without a concrete mechanism for their longevity, the entire concept rests on a shaky foundation. The second major problem is observability. If our galaxy is teeming with countless wormholes, each with the mass of a small asteroid or planet, we should have detected them by now through a phenomenon called gravitational microlensing. When a massive, compact object passes in front of a distant star, its gravity acts like a lens, bending the star's light and causing a temporary, characteristic brightening. Astronomers have conducted extensive microlensing surveys to search for exactly this signature, hoping to find the population of massive compact halo objects, or MACHO, that were once a candidate for dark matter. These surveys have largely ruled out such objects as the primary source of dark matter. If a vast number of wormholes were out there, they should have revealed themselves through these lensing events, but no such evidence has been found. Furthermore, these wormholes would need to be almost perfectly dark. They couldn't be actively accreting matter or emitting radiation, or we would have detected their energetic signatures. This requires them to exist in near total isolation, not interacting with the gas and dust that fills galactic space. While not impossible, it adds another layer of fine-tuning to an already speculative proposal. Despite these formidable obstacles, the theory remains a captivating thought experiment. It challenges us to think creatively and to remember that the universe often holds surprises that defy our conventional expectations. It serves as a crucial reminder that until we definitively identify dark matter, all possibilities, no matter how strange, deserve a moment of consideration in our quest to understand the hidden architecture of the cosmos. Now, let's bring this cosmic scale down to the quantum realm, where the bizarre rules of the subatomic world might offer a completely different perspective on how wormholes could be used. This brings us to a theory that connects the grand geometry of general relativity to the spooky strangeness of quantum mechanics, the idea of quantum teleportation through wormholes. We have an established real-world protocol called quantum teleportation that scientists actually perform in labs today. It allows the exact quantum state of a particle, its unique identity, like its spin or polarization, to be instantly recreated in a distant partner particle. But here's the crucial part that often gets misunderstood in science fiction. It does not teleport the particle itself, nor does it allow for faster-than-light communication. The standard process requires a few key ingredients. First, you need a pair of entangled particles, our old friends from the EPR paradox. Let's call them particle A and particle B. You take particle B to a distant location while keeping particle A with you. Now you have a third particle, particle C, which carries the quantum state you want to teleport. You then perform a special joint measurement on particle A and particle C right where you are. This measurement has two effects. It destroys the original state of particle C, and it instantly affects the state of the entangled partner, particle B, no matter how far away it is. However, the outcome of your measurement is random. To actually reconstruct the original state of particle C at the location of particle B, you must send the results of that measurement the old-fashioned way using a classical, slower-than-light communication channel like a radio signal. The person on the other end uses that instruction manual to perform a specific operation on particle B, which then becomes a perfect replica of what particle C once was. This is where the ER equals EPR conjecture throws a geometric hand grenade into our understanding. It proposes that this entire intricate dance isn't just a mysterious quantum link. It suggests that the two entangled particles, A and B, are physically connected by a microscopic wormhole and Einstein-Rosen bridge. In this breathtaking view, the act of quantum teleportation isn't just an abstract transfer of information. The information that defines particle C isn't being sent as a signal. It is literally traveling through this Planck-scale wormhole that already exists between A and B. The classical communication we send is merely the key that unlocks the door on the other side, telling the recipient how to interpret the information that has already arrived through the geometric shortcut. This fundamentally blurs or perhaps even erases the line between communication and transportation. In our everyday world, sending a message and sending an object are two entirely different processes. But if ER equals EPR is correct, then at the most fundamental level of reality, sending quantum information is a form of transportation through spacetime. The wormhole provides the physical pathway. This provides a powerful geometric picture for how quantum information is transferred, transforming it from a puzzling, non-local phenomenon into a concrete journey through a physical bridge. It offers a potential language to describe quantum gravity, suggesting that the weirdness of quantum entanglement and the warping of spacetime are two sides of the same cosmic coin, forever intertwined in the fabric of the universe. But let's say we overcome the immense obstacles of stability and engineering. We've found a stable wormhole, or perhaps we've even built one. The next challenge is arguably just as daunting, figuring out how to actually use it. Navigating a wormhole would be the ultimate exercise in cosmic blind faith. Unlike a tunnel on Earth where you can see the light at the end, a wormhole's exit is completely hidden from view until the moment you pass through. Its two mouths could be separated by billions of light years of space, or worse, by billions of years of time. The fundamental, terrifying question for any potential traveler is shockingly simple: which way is out? Imagine floating before the swirling vortex of a wormhole mouth. It offers no clues. Peering into it, you wouldn't see a scenic view of another world. The extreme gravitational lensing and warping of light would likely create a chaotic, kaleidoscopic distortion, a mesmerizing but utterly uninformative display. You would have absolutely no visual confirmation of your destination. Stepping through would be the ultimate leap into the unknown. You might emerge in the serene void between galaxies, or you could materialize instantly in the searing inferno of a star's corona, or worse, in the path of a relativistic jet spewing from a hungry black hole. Without a reliable map, wormhole travel would be a game of cosmic Russian roulette. This is where the theoretical field of wormhole cartography comes in. How could we possibly map these cosmic shortcuts? The first and most straightforward method would be to send through unmanned probes. We would need to develop incredibly robust drones capable of surviving the tidal forces of the transit and equipped with a way to send a signal back through the wormhole to us. This is its own profound challenge, as any signal, whether it's light or radio waves, would have to travel back through the wormhole itself. If the probe emerges 10,000 light-years away, but the wormhole acts as an instantaneous bridge, could it send a signal that arrives back at our end just moments after it left? The physics of communication through a space-time shortcut is a fascinating puzzle in itself. A successful probe would send back a data stream of its location, plotting its celestial coordinates, analyzing the local environment, and perhaps most crucially, stamping its data with the cosmological time. This last part is vital because you wouldn't just need to know where you are, but when you are. Beyond physical probes, more exotic mapping theories involve analyzing the wormhole's quantum signature. The premise of the ER equals EPR conjecture suggests that a wormhole is essentially a manifestation of quantum entanglement on a gigantic scale. If this is true, then each mouth of the wormhole might carry a specific, detectable quantum signature, a unique fingerprint of its connection to its twin. Sophisticated instruments placed near the entrance could, in theory, read this signature and decode information about the other end's properties, perhaps even its approximate location in spacetime, without ever having to send anything through. It would be like scanning a barcode that contains the cosmic coordinates of its linked pair. The consequences of failed navigation are the stuff of both scientific caution and science fiction horror. A miscalculation could strand a crew not just far from home, but in a completely different epoch. They could emerge during the early, violent days of the universe, just after the Big Bang, or in the far future during the cold, dark era of heat death. An error in spatial coordinates could be just as catastrophic. Emerging within a planetary system could mean instant collision with an unseen object. Or consider the chilling possibility of arriving in a region of space that is about to experience a cataclysm, like a nearby supernova, whose light, the warning signal of its explosion, hasn't even reached the location of your original wormhole mouth yet. You would have no advance warning, stepping from safety directly into an apocalypse. This inherent uncertainty transforms the wormhole from a simple doorway into a profound existential test, demanding not just advanced technology, but incredible courage from those who would dare to be the first ones through. To understand just how early in the universe's story these structures might have formed, we need to wind the cosmic clock back almost all the way to the very beginning. We're talking about a time so incredibly brief it defies human comprehension, the Planck epoch. This is the period from time 0 up to approximately 10 to the negative 43 seconds after the Big Bang. At this moment, the entire observable universe was compressed into a space far smaller than a single atom, and the four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, were believed to be unified into a single superforce. The energy densities were so extreme that the classical laws of physics as we know them break down completely. Here, the fabric of space-time itself was not smooth and continuous, but a seething, chaotic foam, constantly bubbling with fluctuations in energy and topology. It is from this ultimate chaos that the first wormholes could have spontaneously emerged, not as constructed objects, but as natural topological features, like wrinkles frozen into the expanding fabric of the newborn cosmos. The potential fate of these primordial tunnels presents a fascinating spectrum of possibilities. The overwhelming majority would have lived incredibly short lives. The moment they bubbled up from the quantum foam, the intense gravitational forces at play would have caused them to pinch off and vanish almost instantaneously, their existence measured in fractions of a Planck time. They would have been ephemeral cosmic fireflies, flickering into and out of reality too quickly to have any lasting effect. However, the theory proposes that a tiny, minuscule fraction of these wormholes might have avoided this immediate demise. How could they have survived? One compelling mechanism involves the very expansion of the universe. The rapid inflationary period that is thought to have occurred immediately after the Planck epoch could have stretched some of these microscopic wormholes to macroscopic sizes before they had a chance to collapse. Imagine a tiny bubble in a piece of taffy. As the taffy is pulled and stretched, the bubble is elongated and enlarged. In a similar way, the violent and exponential expansion of space itself in those first moments might have yanked on these nascent wormholes, inflating them from quantum-scale curiosities to structures that could, in theory, be large enough to traverse. Another potential stabilization method harks back to the exotic matter problem. The same quantum fluctuations that spawned the wormholes could have also generated minute amounts of the negative energy density required to prop them open. If this exotic matter became threaded through the wormhole's throat during its formation, it could have acted as a built-in support system, allowing it to resist the powerful urge to collapse. The survival of even a handful of these ancient relics would mean that woven into the fabric of our modern universe are ghostly tunnels, fossils from the first moments of creation, potentially connecting vastly distant regions of space that were once in intimate contact during the Big Bang. The hunt for these cosmic fossils is one of the most exciting challenges in modern astrophysics. How do you find something that is, by its very nature, a nearly invisible tunnel through space-time? Astronomers have proposed several ingenious methods. The most promising involves gravitational lensing. Any object with mass warps the space around it, bending the path of light from distant background objects. A wormhole possessing significant mass would act as a gravitational lens. However, its signature would be distinct from that of a black hole or a star. Because a wormhole has two mouths connected by a throat, its lensing effect might create a unique double image or a peculiar pattern of light distortion that sophisticated telescopes could potentially detect. We would be searching for anomalies in the sky, strange, warped images of galaxies that can't be explained by the gravitational pull of conventional matter. An even more subtle detection method looks to the oldest light in the universe, the cosmic microwave background radiation. This faint glow is the remnant heat from the Big Bang, and it contains tiny temperature fluctuations that map the density variations of the early universe. A stable, macroscopic primordial wormhole existing in the early cosmos would have represented a significant disturbance in the density of matter and energy. Its gravitational influence could have left a faint, telltale imprint on this cosmic background radiation, a specific circular pattern of hot or cold spots that would stand out from the random fluctuations. Researchers are actively developing algorithms to scour the exquisite maps of the CMB produced by telescopes like Planck, searching for these subtle, ghostly fingerprints. Finding one would be more than just evidence for wormholes. It would be a direct window into the quantum gravity era, offering unparalleled insight into the universe's turbulent and mysterious birth. But if the universe truly is a hologram projected from a distant boundary, could that screen be just one of countless others? This brings us to a theory that stretches the very definition of reality, pushing the concept of wormholes to its absolute limit. We've explored how these cosmic tunnels might connect distant points within our universe, or even different moments in time. But what if their most profound function is to serve as bridges to realms beyond our own, gateways to the multiverse? The idea of a multiverse, a vast collection of parallel universes, isn't just science fiction. It emerges naturally from two of our most successful scientific theories, quantum mechanics and inflationary cosmology. First, consider the many worlds interpretation of quantum mechanics proposed by Hugh Everett in the 1950s. Every time a quantum event occurs with multiple possible outcomes, like an electron being measured as spinning up or down, the theory suggests the universe doesn't choose one outcome. Instead, it splits. One universe is created where the electron is spinning up, and another, completely separate universe branches off where it is spinning down. This process would happen constantly, creating an unfathomably vast tree of branching realities. Now, imagine if a naturally occurring or artificially created wormhole didn't just tunnel through space, but also through this branching structure of reality. It could, in theory, connect our present to a branching point in the past, offering a tunnel to a universe where a different quantum outcome occurred. You could step into a reality where every coin toss in history came up the opposite way, where every decision ever made had a different result. The second multiverse theory comes from cosmic inflation. This model proposes that our universe is just one bubble in a frothing, eternal cosmic foam. The rapid expansion of space during the Big Bang could have happened in multiple regions, each giving rise to its own distinct bubble universe with its own unique properties. These bubbles might be endlessly budding off from a greater multiversal substrate. In this breathtaking scenario, wormholes could be the threads stitching this cosmic quilt together. They might be natural formations left over from the inflationary era, or they could be structures that form at the boundaries where two expanding bubble universes briefly touch. A wormhole could serve as a permanent umbilical cord, a stabilized tunnel linking the interior of our bubble to the interior of another. The implications of such a connection are almost beyond comprehension. If you could traverse a multiversal wormhole, you might not just visit a different location. You might enter a universe with entirely different fundamental constants. Imagine a world where the force of gravity is 100 times stronger, making every planet a crushing, high-gravity prison, or a universe where the speed of light is only 30 miles per hour, making relativity an everyday experience. You could find realms where atoms never formed, where life is based on an entirely different chemistry, or where the very concept of time is unlike anything we can imagine. Such travel would be the ultimate exploration, but also the ultimate risk. Without any shared physical laws, our technology, our biology, and our very existence might be incompatible with the reality on the other side. It's crucial to emphasize that this remains one of the most speculative frontiers in all of theoretical physics. There is no direct evidence for the existence of other universes, let alone wormholes connecting to them. The energies required to stabilize a tunnel between such fundamentally different domains are unimaginable, and the cosmic censorship hypothesis might still forbid such a direct connection. Yet, the mathematical possibility continues to inspire physicists and captivate our imagination, suggesting that our universe might not be a solitary island, but one shore in an infinite archipelago of realities, all potentially linked by the most mysterious structures in the cosmos. Yet for all the ingenious theories about building and using these cosmic tunnels, one of the most brilliant minds of our time proposed a fundamental reason why they might forever remain locked. The late physicist Stephen Hawking looked at the idea of wormhole time machines and saw not just an engineering challenge, but a profound threat to the logical foundation of the universe itself. He famously formulated what he called the chronology protection conjecture, an elegant and powerful proposition that the laws of physics inherently contain a built-in mechanism to prevent time travel to the past, thereby protecting the chronology of cause and effect from the paradoxes that would shatter it. Hawking's argument wasn't based on a lack of imagination, but on a deep understanding of quantum mechanics. He asked a simple, devastating question. If time travel to the past is possible, even in theory, then where are all the tourists from the future? His conjecture provides a potential answer. He proposed that any attempt to create a time machine, such as by manipulating a wormhole to form a closed time-like curve, would trigger a runaway reaction from the quantum vacuum that would inevitably destroy the wormhole at the precise moment it became usable. The mechanism for this cosmic self-defense system is as fascinating as it is final. In the bizarre world of quantum physics, empty space is not truly empty. It is a seething sea of virtual particles that constantly flicker into and out of existence. Under normal circumstances, these fluctuations are subtle and average out to zero. However, Hawking calculated that the warped spacetime geometry right at the throat of a wormhole on the verge of becoming a time machine would act like a monstrous amplifier for these quantum fluctuations. A single virtual particle looping through the closed time-like curve again and again would effectively experience an infinite amount of time, allowing its energy to build up in a catastrophic positive feedback loop. This wouldn't be a small burst of energy. The calculations suggest it would become an infinitely intense surge of radiation, a firewall of pure energy that would either force the wormhole to collapse or create a singularity that would seal the door to the past forever, just before the first paradoxical event could occur. The critical question then becomes whether Hawking's conjecture is an unbreakable law of nature or merely the ultimate engineering puzzle. Some physicists argue that chronology protection is a fundamental principle, as vital to the consistent functioning of the universe as the speed of light limit. They see it as nature's ultimate paradox prevention service, a non-negotiable rule woven into the fabric of reality. Others, however, view it as a challenge to be solved. They speculate that a civilization with a godlike command of physics and technology might find a way to somehow dampen or divert these quantum fluctuations, perhaps by manipulating the exotic matter lining the wormhole to counteract the energy surge. They imagine a future where we could bleed off the excess energy or fine-tune the system to avoid triggering the feedback loop altogether, essentially outsmarting the universe's own security system. This debate sits at the very heart of our understanding of physics. It forces us to ask if the paradoxes of time travel are mere puzzles for us to solve, or if they are fundamental errors that the universe is hardwired to correct. Hawking's conjecture stands as a formidable guardian at the gates of time, a reminder that some doors, once opened, might lead not to wonder but to the dissolution of reality itself. If navigating the macroscopic twists of general relativity feels like a cosmic challenge, we must now plunge into the quantum realm, where the very idea of spacetime is rewoven at its most fundamental level. This journey brings us to string theory, the most ambitious framework in modern physics, which seeks to marry Einstein's gravity with quantum mechanics by proposing that the universe's tiniest constituents are not point-like particles but incredibly small, vibrating strings. In this rich theoretical landscape, wormholes are not merely tunnels through the four-dimensional fabric of spacetime we experience. They are far more exotic structures, deeply woven into the theory's prediction of extra-spatial dimensions, and they may hold the key to resolving some of physics' most stubborn paradoxes. String theory posits that our universe of three spatial dimensions and one time dimension is actually a membrane or brain, floating in a higher dimensional arena known as the bulk. In this view, a wormhole could be a tunnel that connects two distant points on our brain, but it could also be a conduit that arcs out through the bulk itself, offering a shortcut that bypasses our familiar dimensions entirely. This reimagining transforms the wormhole from a simple cosmic subway into a multi-dimensional elevator, a journey that might take millions of years traveling along the surface of our brain could be nearly instantaneous by dipping into the higher dimensional space, providing an elegant geometric explanation for the shortcut. The concept becomes even more profound when we consider the string theory landscape, a vast, multidimensional terrain of possible universes, each with its own physical constants and laws. Our universe, with its specific values for gravity and the mass of an electron, is just one valley in this colossal cosmic mountain range. Theorists like Leonard Susskind have proposed that wormholes could be the pathways connecting these different valleys. They might serve as bridges between entirely separate universes within the multiverse, each with its own unique vacuum state. This suggests a cosmos of unimaginable richness, where the tunnels through reality could lead not just to other stars, but to other sets of physical laws altogether. Perhaps the most impactful application of string theory wormholes has been in the fierce debate over the black hole information paradox. You'll recall that Stephen Hawking's calculation suggested information swallowed by a black hole is lost forever when the whole evaporates, violating a core quantum rule. This created a paradox that divided physicists for decades. Susskind and others used the tools of string theory to propose a stunning resolution: wormholes. The theory suggests that the information isn't actually lost inside the black hole. Instead, it is secretly transmitted via microscopic wormholes to the Hawking radiation being emitted outside. These wormholes, acting as quantum entanglement manifolds, would ensure that every bit of information that falls in is intricately encoded into the outgoing radiation, preserving the total information of the universe. This idea was a precursor to the broader ER=EPR conjecture, providing a concrete string theoretic mechanism for how space-time connectivity and quantum entanglement are fundamentally linked. It offers a vision of reality where the fabric of space itself is embroidered with an unfathomably complex web of these tiny bridges, ensuring the consistency of the cosmos from the smallest quantum event to the largest galactic scale. Yet the quest to unite quantum mechanics with gravity leads us to one of the most intense and baffling paradoxes in modern physics, a puzzle so severe it threatens to tear apart our understanding of reality at the event horizon of a black hole. This is the infamous black hole firewall paradox, and its potential resolution hinges entirely on the existence of wormholes. The paradox begins with a seemingly straightforward question: what would actually happen to you if you fell into a black hole? For nearly a century, general relativity provided a serene, if grim, answer. According to Einstein's theory, if you were to cross the event horizon of a sufficiently large black hole, you wouldn't feel anything dramatic at all. The horizon itself would be a smooth, unremarkable region of space. You wouldn't see it or feel it. The principle of equivalence, a cornerstone of general relativity, assures us that a freely falling observer should experience the laws of physics just as they would in empty space. Your journey would continue undisturbed until you were eventually stretched and compressed by the ever-strengthening tidal forces on your way to the central singularity. But when we apply the rules of quantum mechanics to this scenario, this peaceful picture completely shatters. In the 1970s, Stephen Hawking made his monumental discovery that black holes are not truly black. They emit radiation due to quantum effects near the event horizon. This Hawking radiation carries away energy, causing the black hole to slowly evaporate and eventually vanish. However, Hawking's calculation also suggested a terrifying problem: the information paradox. The radiation appears to be completely random, containing no information about the intricate details of the matter that originally fell in. This violates a fundamental law of quantum mechanics, the principle of unitarity, which states that information must never be lost. It can be scrambled, but it must always be preserved in principle. In 2012, a team of physicists including Ahmed Olmary, Donald Maroff, Joe Polchinski, and James Sully, now known by their initials at MPS, pushed this paradox to its logical extreme. They asked a devastating question. If the Hawking radiation is truly random and carries no information, then what must be happening at the event horizon to make that possible? Their rigorous mathematical analysis led to a horrifying conclusion. For the information to be preserved in the Hawking radiation outside the black hole, for the laws of quantum mechanics to remain intact, the entanglement connections between particles just inside and just outside the horizon must be severed. This violent breaking of entanglement would release an astronomical amount of energy. The result, the event horizon would not be a smooth, empty space. It would be transformed into a searing wall of fire, a barrier of ultra-high energy particles that would instantly incinerate anything or anyone crossing it. This is the firewall paradox, a direct and brutal conflict between the smooth geometry demanded by general relativity and the information preservation demanded by quantum mechanics. You cannot have both. One of our most cherished theories must be wrong at the most fundamental level. This is where the elegant but radical ER equals EPR conjecture enters, offering a breathtaking escape from this impossible choice. The conjecture, as proposed by Juan Maldacena and Leonard Susskind, posits that entangled particles are not just mysteriously linked. They are physically connected by microscopic Einstein-Rosen bridges or wormholes. Apply this idea to the black hole. The Hawking radiation escaping into space is made of particles. Each of those particles is entangled with a partner particle that falls into the black hole. According to ER equals EPR, each of these entangled pairs is connected by a tiny wormhole. This means the interior of the black hole is not some isolated prison cut off from the universe. It is intricately woven through a vast web of Planck-scale wormholes to the very radiation that is streaming away from it. This changes everything about the firewall problem. The MPS argument assumed that the entanglement between the inside and outside had to be broken, creating the fiery energy release. But if a wormhole connects the two, then the entanglement is not a fragile, ghostly link that needs to be severed. It is a robust geometric connection. There is no sharp, classical event horizon where information is lost and physics breaks down. Instead, the horizon becomes a fuzzy, quantum mechanical transition zone, threaded through with these microscopic bridges. The information about what fell in doesn't stay trapped inside, nor is it destroyed at a firewall. It is seamlessly transferred through the wormhole network to the outgoing radiation, preserving it perfectly. The infalling observer, from their perspective, would still experience the smooth spacetime promised by Einstein, because the wormholes ensure that the horizon is never a singular, violent boundary. The paradox is resolved not by choosing between quantum theory and relativity, but by uniting them through the geometry of wormholes, making these cosmic tunnels absolutely essential for the logical consistency of the universe under its most extreme conditions. But even with the promise of a cosmic web of entanglement, the challenge of deliberately constructing a stable passageway remains the ultimate test of a civilization's mastery over reality itself. To move from discovering a natural wormhole to forging one from nothing is a leap of ambition that staggers the mind. The energy budget alone for such a project is almost beyond calculation. Theorists estimate that to create a wormhole with a throat just 1 meter wide, you would need to concentrate a quantity of negative energy equivalent to the total energy output of a star like our Sun for a period of several years. We're not talking about burning fuel in a furnace. We're talking about manipulating the fundamental mass energy of a star, compressing and converting it into a form of exotic matter with the sole purpose of warping spacetime against its own will. How could such an inconceivable feat of engineering possibly be achieved? One speculative method involves the ultimate cosmic power plant, a rotating black hole. The Kerr black hole, as we discussed, contains an enormous amount of rotational energy that, in theory, could be extracted through a process known as the Penrose process. A sufficiently advanced civilization might learn to tap this incredible power source, not for electricity, but to fuel the creation of a space-time anomaly. They could, perhaps, use focused beams of this harvested energy to create and stabilize a region of intense negative energy density, effectively prying open a new wormhole in the fabric of the universe. The black hole would become a forge, its unimaginable gravity and spin providing the anvil and the hammer to shape reality itself. Another approach is even more subtle and speaks to the quantum origins of space-time. If the universe is indeed a tapestry woven from microscopic wormholes, as the holographic principle suggests, then perhaps construction isn't about building from scratch, but about amplifying what is already there. This leads to the fascinating garden hose theory. Imagine if we could, through some advanced quantum gravity technology, create or locate a single, stable, traversable wormhole, but one that is only the size of the Planck length, a billionth of a trillionth of a centimeter across. This microscopic gateway would be useless for travel, but it would exist. The theory proposes that we could then carefully feed it by pumping a controlled stream of exotic matter and energy into this minuscule throat. We could theoretically coax it to inflate slowly and carefully, like blowing up a cosmic balloon or unspooling a garden hose. Over time, with immense patience and precision, this subatomic tunnel could be expanded to a macroscopic size, a process of nurturing a space-time connection rather than violently wrenching one into existence. The sheer scale of these proposals immediately confirms that such an endeavor resides firmly in the domain of far future science fiction. The precision required is as daunting as the energy. Manipulating space-time on this level isn't like engineering steel and concrete. It's about controlling the quantum foam itself, directing energies that could easily tear apart the very structure you're trying to build. A miscalculation wouldn't just lead to a collapsed tunnel. It could unleash gravitational shocks or create a runaway singularity. The act of creation is inextricably linked with the potential for catastrophic failure, a reminder that the power to bend the universe to our will carries with it the responsibility to understand it completely. This profound silence, this cosmic quiet that defines our night sky, leads us directly to one of the most haunting questions in all of science, the Fermi paradox. Coined after a casual lunchtime remark by physicist Enrico Fermi in the 1950s, it asks a deceptively simple question. Given the overwhelming probability that the universe is teeming with planets capable of supporting life, and given the immense age of the galaxy, which has provided ample time for intelligent civilizations to arise and spread, then where is everybody? Why do we see no signs, no structures, no signals, and no visitors? Wormhole theory offers a pair of compelling and deeply contrasting solutions to this great silence, one offering a hopeful future and the other a terrifying warning. The first possibility is that advanced civilizations are not just out there, but are everywhere. They have simply transcended the need for the slow, plodding methods of interstellar travel that we are only beginning to conceive of. Think about our own civilization. A few centuries ago, crossing an ocean was a perilous, months-long journey in a wooden ship. Today, we board a metal tube and cross that same distance in a matter of hours. The paradigm of travel was completely upended. Now, scale that up to a galactic level. A species millions of years more advanced than us would likely view our concepts of generation ships and sublight probes the same way we view canoes. Their transportation network wouldn't be based on moving through space. It would be based on bypassing it entirely through a stable, interconnected wormhole network. This would create a kind of cosmic internet or subway system, a series of fixed gateways linking star systems and perhaps even galaxies. If you had access to this network, you wouldn't waste centuries traveling the bleak, empty void between stars. You would simply step through a portal and emerge instantly at your destination. This provides a perfect explanation for why we see no evidence of their passage. We are scanning the skies for radio signals and Dyson spheres, but we should perhaps be looking for the subtle, telltale gravitational lensing signatures of these fixed wormhole mouths, which would be virtually invisible to our current technology. The galaxy could be buzzing with activity, but it's all happening on a subspace highway that is completely hidden from our view. We are, in this scenario, like an isolated tribe deep in the rainforest, completely unaware of the global network of airplanes flying high above the canopy, connecting a civilization we cannot even imagine. However, this optimistic view has a dark and deeply unsettling flip side, one that touches on the concept of the Great Filter. The Great Filter is a hypothesized stage in the evolution of life that is so improbably dangerous or difficult that it prevents virtually all civilizations from progressing to the point of interstellar colonization. The terrifying question is whether the creation of stable wormholes is itself that filter. The energy and exotic matter requirements we've discussed are so far beyond our current understanding that the process of creating a wormhole might be the ultimate scientific gamble. The forces involved in twisting spacetime into a stable knot could be inherently unstable, like trying to balance a pencil perfectly on its point. The slightest error in the containment of the negative energy fields or the geometry of the throat could trigger a catastrophic failure. This failure might not be a simple explosion. Some theorists, like the renowned physicist Stephen Hawking, warned about the potential for a phenomenon called vacuum decay. Our universe exists in what is known as a false vacuum, a state that is stable but not the absolute lowest energy state possible. A high-energy event, like the collapse of a manufactured wormhole, could theoretically act like a spark in a dry forest. It might create a tiny bubble of true vacuum that would then expand outward at the speed of light, fundamentally rewriting the laws of physics in its wake. The constants of nature, the strength of gravity, the mass of an electron would change instantly and permanently within this expanding bubble. For any life caught in its path, it would be an instantaneous and silent end, not with a bang, but with a quiet rewriting of reality itself. This could be the reason for the Great Silence, not because civilizations choose to be quiet, but because every single one that reaches the technological threshold to attempt cosmic engineering inadvertently triggers its own annihilation, leaving behind a galaxy full of ghost worlds and silent ruins, a permanent monument to a challenge that no species can survive. The Fermi paradox then becomes a cosmic cautionary tale, and the wormhole transforms from a symbol of hope into a potential universal emergency brake on intelligent life. Yet for all their potential to rewrite the rules of distance, it's crucial to clarify a profound and often misunderstood point about how wormholes truly function. A journey through one of these cosmic shortcuts is not, in the strictest sense, faster than light travel. That phrase conjures images of a starship igniting its engines and accelerating beyond the speed of light, blatantly violating Einstein's sacred cosmic speed limit. A traversable wormhole offers something far more clever and subtle, a magnificent loophole in the laws of physics that achieves the same result without ever breaking the rules locally. Think of it this way: imagine you need to get from the bottom of a tall mountain to the top. The long, winding road that snakes its way up the slope is 20 miles long. If you were to drive that road at the legal speed limit of 60 miles per hour, your journey would take 20 minutes. But what if, instead of taking the road, you discovered a perfectly straight tunnel that went directly through the heart of the mountain? This tunnel is only 1 mile long. You drive through it at the exact same speed limit of 60 miles per hour, and your journey takes just 1 minute. To an observer watching from a distance, you seemingly arrived at the top impossibly fast, far quicker than anyone driving the road ever could. but you never once exceeded the speed limit. You simply took a much shorter path. This is the elegant principle behind wormhole travel. The speed of light, approximately 300,000 kilometers per second, is the ultimate speed limit for any object moving through local spacetime. Inside the wormhole's throat, your spacecraft would be moving at perfectly normal sublight speeds. You might be cruising along at 99% the speed of light, but you are still obeying the law. The magic isn't in your velocity, it's in the geometry of the tunnel itself. The wormhole warps the fabric of the universe, bringing two incredibly distant points into such close proximity that a short, sub-light speed journey through the throat covers a distance that would have taken light itself thousands or millions of years to cross through normal space. You effectively achieve faster-than-light travel times without ever engaging in faster-than-light motion. This distinction is vital because it resolves one of the most troubling paradoxes of relativity: time dilation. If you were to truly travel between stars at near light speeds through normal space, you would experience the strange effects of Einstein's time dilation. A journey to a star 100 light-years away might feel like only a few years to you and your crew, but when you return to Earth, centuries would have passed. Everyone you knew would be long gone. Wormhole travel, if the mouths are kept synchronized, could potentially avoid this heartbreaking time loss. Because your local speed never approaches the light barrier within the tunnel, the extreme relativistic effects are minimized. You could pop over to Alpha Centauri for a visit and return to an Earth that has aged only the same few days or weeks that you experienced, making interstellar civilization and even round-trip exploration a genuine possibility without the tragic cost of time. It's a loophole of cosmic proportions, allowing us to honor the letter of Einstein's law while still daring to achieve its spirit. But what exactly is this exotic matter we keep referring to, and how could something with such bizarre properties possibly hold the key to a stable wormhole? The answer lies in a concept that seems to defy all our everyday experience: negative mass. We are so accustomed to the behavior of positive mass that the idea of its opposite is almost impossible to picture. If you were to push a regular object, a book, a ball, a spaceship, it accelerates away from you. This is Newton's second law, the foundation of classical mechanics. Now imagine an object with negative mass. If you pushed it, the equation would flip. It would experience the force and accelerate, but not away from you. It would, astonishingly, accelerate toward you. It would exhibit behavior that is the complete opposite of everything we know, reacting to forces in a way that seems utterly inverted and counterintuitive. This bizarre property translates directly into the realm of gravity. According to Einstein's general relativity, mass and energy tell spacetime how to curve. Positive mass, like that of a planet or a star, creates the familiar attractive gravity that warps spacetime inward, forming gravity wells. Negative mass would do the opposite. It would warp spacetime outward, creating a kind of gravitational hill. This repulsive gravity is the exact counterforce needed to solve the wormhole stability problem. The natural tendency of a wormhole's throat is to collapse under its own intense gravitational pressure, snapping shut like a rubber band. To keep it propped open, you need something pushing back with equal and opposite pressure. Lining the throat with negative mass exotic matter would be like installing a network of anti-gravity support beams, generating a persistent outward push that fights the inward crush, allowing the tunnel to remain open and traversable. The question of whether such a substance can truly exist is one of the most heated debates in theoretical physics. On one hand, the equations of quantum field theory do not explicitly forbid it. Certain quantum effects, like the Casimir effect we discussed, demonstrate that regions of negative energy density are possible, albeit on a tiny scale. This suggests that the vacuum of space itself has a rich structure that permits these exotic states. Some physicists are optimistic that with a deeper understanding of quantum mechanics, we might discover a form of stable, condensed matter that exhibits these properties on a macroscopic scale. It could be a new state of matter, a quantum fluid with negative mass that we simply haven't discovered how to create or stabilize yet. On the other hand, many scientists are deeply skeptical, arguing that negative mass leads to a host of logical nightmares and paradoxes that violate fundamental principles of causality. For instance, if you had a positive mass and a negative mass object next to each other, the negative mass would be repelled by the positive mass's gravity, while the positive mass would be attracted to the negative mass. This could create a system where the two objects chase each other in a perpetual acceleration, gaining infinite speed and energy from nothing, which would blatantly violate the conservation of energy. This is known as the runaway motion paradox, and it suggests that large, stable chunks of negative mass might be inherently impossible, as they would lead to an unstable universe. The discovery of stable negative mass matter would be a scientific revolution on par with the discovery of quantum mechanics itself. It would force a complete rewrite of our understanding of quantum field theory, gravity, and the very nature of the vacuum. It would prove that the universe permits forms of matter that are not just unknown, but are fundamentally alien to our experience, operating under a completely different set of physical rules. Finding it would not just open the door to wormhole engineering, it would shatter the doorframe and reveal an entirely new wing of physics that we are only beginning to imagine. Until then, negative mass remains one of the most tantalizing and controversial ideas at the frontier of our knowledge, a key that could unlock the cosmos or a phantom that exists only in the elegant script of our mathematics. Even the most perfectly engineered wormhole, held open by a delicate balance of exotic matter, might not be a permanent fixture in the cosmos. It could face the same slow, inexorable fate that awaits even the most massive black holes' evaporation. This theory draws a direct parallel to one of Stephen Hawking's most profound discoveries, applying the same quantum mechanical principles to these cosmic tunnels and suggesting that all wormholes may have a finite lifespan, slowly leaking energy away over near-eternal timescales. To understand how this works, we need to revisit the bizarre behavior of the quantum vacuum at the wormhole's most vulnerable point, its throat. As we've discussed, empty space is not truly empty. It is a seething foam of virtual particle pairs constantly flickering into existence. Normally, these pairs annihilate each other almost instantly. However, in regions of intense gravitational curvature, like the mouth of a black hole or the throat of a wormhole, this delicate dance can be violently disrupted. The immense tidal forces can tear these particle pairs apart before they have a chance to recombine. One particle is snatched away by the gravitational field while its partner escapes into space. For a black hole, this process results in Hawking radiation, a slow leak of energy that causes the black hole to gradually lose mass and over trillions of years evaporate completely. A similar process could occur at the narrowest point of a wormhole throat. The intense warping of spacetime there could act as a catalyst, separating these virtual particles. One particle might fall into the negative energy region maintained by the exotic matter, while the other escapes into the wider universe. This escaping particle carries away a tiny amount of energy. While a single such event is immeasurably small, over cosmological timescales, millions, billions, or even trillions of years, this slow trickle of radiation would add up. The wormhole would very gradually lose the very exotic energy that is holding it open. It's like a magnificent suspension bridge where the individual steel strands of its cables are slowly, one by one, being weakened by corrosion. For a wormhole stabilized by exotic matter, this evaporation isn't just a slow energy loss, it's a direct attack on its structural integrity. The negative energy density is what provides the crucial outward pressure against collapse. As this energy slowly leaks away, that counter-pressure weakens. The throat, constantly battling the immense gravitational forces trying to crush it shut, would begin to narrow. The balance would tip. Eventually, the inward crush would overcome the weakened outward push, and the wormhole would undergo a pinch-off. The throat would snap closed, severing the connection between its two mouths forever. The two ends would then likely collapse into separate black holes or simply vanish, leaving no trace of the cosmic shortcut that once was. This introduces a staggering new challenge to the dream of a permanent interstellar transportation network. It suggests that even if a civilization mastered the technology to create a wormhole, they wouldn't just be building a structure, they would be fighting a relentless, fundamental law of quantum physics. Maintaining a wormhole would require not only a one-time investment of energy, but a continuous, perhaps eternal, effort to replenish the exotic matter that is slowly but inevitably evaporating away. It would be like trying to keep a leaky boat afloat by constantly bailing water. Stop for even a moment, and the entire vessel will eventually succumb to the sea. This theory also paints a fascinating picture for any natural wormholes we might one day discover. If they exist, they are likely not the pristine, eternal tunnels of science fiction. They would be ancient relics, billions of years old, slowly decaying. We might find them in the final stages of evaporation, their throats already dangerously narrow and unstable, on the very brink of pinching closed. Traveling through such an ancient structure would be the ultimate risk, a race against a clock set by the quantum decay of the universe itself, where the tunnel could collapse at any moment, stranding a traveler in an unknown time or place or erasing them from existence entirely. For generations, the wormhole has been more than a scientific hypothesis. It has been a powerful narrative engine for some of our most ambitious science fiction, offering filmmakers and writers a convenient gateway to the stars. These cinematic portrayals have shaped our collective imagination, but they often take significant creative liberties, simplifying the mind-bending physics into a more palatable and visually spectacular form. Consider the iconic Stargate from the film and television franchise of the same name. It presents a wormhole as a stable, shimmering pool of liquid energy, a fixed doorway that whooshes open with the dialing of an address, allowing for instantaneous and seemingly effortless travel between worlds. This vision is incredibly clean and user-friendly. There's no discussion of terrifying tidal forces, no need for exotic matter generators, and certainly no risk of the tunnel collapsing mid-journey. The technology is treated as a perfected tool, a cosmic subway system that is as reliable as it is mysterious, focusing the drama on the destinations rather than the daunting physics of the journey itself. The Marvel Cinematic Universe offers another highly stylized version with the Bifrost from the Thor films. Here, the wormhole is reimagined as a radiant, rainbow-hued energy bridge, a divine conduit controlled by the advanced technology of Asgard. While it captures the awe-inspiring spectacle of a connection between realms, it operates more like a directed energy beam than a gravitational phenomenon. It effortlessly transports individuals and objects with pinpoint accuracy, ignoring the complexities of space-time geometry and the horrifying gravitational shear that a real wormhole's entrance would likely exhibit. These portrayals prioritize mythic grandeur and narrative pace over scientific plausibility, creating a sense of magical wonder that is compelling storytelling, if not accurate physics. In stark contrast, Christopher Nolan's film Interstellar stands as a rare attempt to ground its science fiction in real theoretical physics, thanks to the involvement of renowned physicist Kip Thorne as a scientific consultant. The film's wormhole, hovering near Saturn, is depicted as a shimmering spherical sphere, a visualization that aligns with the theory that a higher dimensional object might appear as a globe to our three-dimensional perception. The interior journey through the wormhole, dubbed the Tesseract, is a chaotic kaleidoscope of distorted starlight and gravitational lensing, a far cry from the calm blue tunnel of Stargate. This portrayal captures the disorienting and non-Euclidean weirdness that a real transit might involve. Furthermore, the film's treatment of the supermassive black hole Gargantua and its time dilation effects is its most celebrated scientific achievement. The hours spent on the watery planet Miller, where every hour equals 7 years back on the ship, is a dramatic but accurate representation of gravitational time dilation as predicted by general relativity. However, even Interstellar takes its artistic licenses. The crew's survival while skimming so close to the event horizon of Gargantua would, in reality, likely be impossible due to the intense radiation and particle jets active black holes possess. The film also sidesteps the problem of what inexplicably created and placed the stable wormhole near Saturn, a mystery that the narrative attributes to benevolent higher-dimensional beings. This highlights the fundamental divide between science fiction and scientific reality. Hollywood requires stable, navigable gateways to tell stories about exploration and adventure. Reality, as dictated by Einstein's field equations, offers only unstable mathematical curiosities that snap shut instantly. The cinematic dream of a wormhole is a finished product, a user-friendly portal. The scientific reality is a daunting engineering puzzle that begins with the near-insurmountable challenge of discovering or creating exotic matter with negative energy density, then shaping it with impossible precision to line a fragile throat, all while preventing a catastrophic collapse or a deadly encounter with a singularity. Sci-fi inspires us to look up and dream of the journey, while science forces us to grapple with the monumental, perhaps impossible, task of building the door. Yet, this creative tension is vital. The fantastical depictions in film and literature capture the public imagination, fueling wonder and inspiring the next generation of physicists to ask, what if we could? They provide the dream, and it is the painstaking work of science that slowly, methodically, tests the boundaries of that dream against the unforgiving laws of the universe. But if these cosmic tunnels are woven into the fabric of reality, how would we ever hope to spot one? The search for a wormhole is the ultimate game of celestial hide and seek, forcing astronomers to become detectives looking for subtle clues written in the language of light and gravity. Unlike a star that shines or a nebula that glows, a wormhole would likely be almost perfectly dark, a silent ghost in the interstellar void. Its detection wouldn't come from the light it emits, but from the bizarre way it warps the space around it. The most promising method for spotting one relies on a phenomenon we already use to study the universe: gravitational lensing. We know that any object with mass bends the path of light passing nearby. A massive galaxy cluster, for instance, can act as a cosmic magnifying glass, distorting the images of galaxies behind it into long, faint arcs. A wormhole would also lens the light from stars and galaxies behind it, but its signature would be utterly unique and distinct from that of a black hole. A black hole, with its single, point-like singularity, typically creates multiple smeared images of a background object arrayed around it. A wormhole with its two connected mouths would create a far more complex pattern. Imagine a bright star situated directly behind a wormhole from our viewpoint. The light from that star would be bent as it passes both mouths. Instead of a single Einstein ring or a pair of images, we might see two complete bright rings of light, nested within each other or sitting side by side, a celestial signature that has no other natural explanation. It would be like seeing a double shadow from a single object, a physical impossibility that would immediately signal the presence of a profoundly strange gravitational anomaly. There's another, even more mind-bending optical effect a wormhole might produce. If one mouth of the wormhole is situated in front of a brilliantly luminous background like the accretion disk of an active galaxy or a dense star field, and the other mouth is floating in relatively empty space in front of us, we could witness something that defies common sense. Light from that bright background would travel through the wormhole and spew out of the mouth in our neighborhood. To our telescopes, it would appear as though a brilliant, star-like point of light is magically glowing in the middle of nowhere, a cosmic mirage with no obvious source. We would see light that originated millions of light years away being projected onto a screen of empty space right in front of us. Identifying such an anomaly would require meticulously mapping the light and cross-referencing its spectral signature with known objects across the universe to find its true, distant origin. Beyond light, the ripples in space-time known as gravitational waves offer another hunting ground. The merger of two black holes creates a very specific gravitational wave signal, a rapidly rising chirp followed by a sharp cutoff once the black holes merge and form a new event horizon. A collision involving a wormhole, however, would be radically different. If two wormholes were to interact or if one were to oscillate violently, it might not produce that clean, final cutoff. The signal could exhibit strange echoes as gravitational waves bounce around inside the exotic geometry of the throats before finally escaping. Alternatively, the unique structure of a wormhole's throat, lined with exotic matter, could vibrate in ways a black hole never could, emitting a continuous, low-frequency hum of gravitational waves, a persistent drone hidden beneath the louder chirps of colliding black holes. While our current observatories like LIGO and Virgo might not be sensitive enough to pick out these subtle fingerprints, next-generation instruments could be tuned to listen for these whispers from the void. The hunt is already underway. Astronomers are meticulously sifting through data from telescopes and gravitational wave detectors, developing sophisticated algorithms to search for these tiny statistical anomalies and weird lensing patterns that could betray the presence of a hidden tunnel. They are looking for the impossible, a shadow where there should be light, light where there should be shadow, or a ripple that doesn't quite fit the pattern. Every strange, unexplained blip in the data is a candidate, a potential doorway waiting to be confirmed. It is a painstaking process, a search for a single cosmic needle in a galaxy-sized haystack, but the potential reward, the first proof that our universe is connected, makes it a pursuit worth every moment. Yet for all the staggering physics and engineering, the most profound challenges posed by wormholes may not lie in the realm of equations and exotic matter, but within ourselves. The ability to manipulate space-time forces us to confront a series of deep, unsettling ethical and philosophical questions that strike at the very core of our understanding of reality, responsibility, and human nature. If time travel is indeed possible through these cosmic tunnels, it unravels our most fundamental concepts of cause and effect. The famous grandfather paradox is more than a logic puzzle. It's a direct assault on the principle of free will. If you can travel back and change an event, were your actions ever truly free, or were they always destined to happen? This suggests a universe that might operate under a principle of self-consistency, where any attempt to alter the past would inevitably fail, making you a pawn in a predetermined timeline. Alternatively, if the many worlds interpretation holds, your actions wouldn't change your own history, but would simply spawn a new, branching reality. This doesn't resolve the philosophical unease. It merely multiplies it, forcing us to ask what moral responsibility we hold for the countless alternate versions of ourselves and the worlds our choices create. The implications expand exponentially if wormholes serve as gateways to a multiverse. Stepping into another universe isn't like visiting another country. It's entering a realm with its own unique history, life, and physical laws. Do we have any right to be there? Would our presence be seen as exploration or as an invasive violation? The potential for exploitation is terrifying. A universe rich in resources but devoid of intelligent life could be strip-mined without a second thought, its unique ecosystems destroyed for short-term gain. A universe with a less advanced civilization could face cultural contamination or even conquest, a dark replay of Earth's colonial history on an interstellar scale. This forces us to develop a completely new ethical framework, a concept of inter-universal rights and responsibilities that acknowledges we are no longer just citizens of a planet or a galaxy, but potential actors on a multiversal stage. Even without leaving our own universe, the power of instantaneous travel would force a radical rethinking of our most basic social structures. The concepts of territory, border, and nation-state become almost meaningless when any point on Earth is just a step away from any other. This could lead to a utopian era of unparalleled connectivity and cultural exchange, erasing the isolation that has fueled so much human conflict. But it could also enable dystopian nightmares of control and surveillance. A government that controls the wormhole network could monitor and control populations with an efficiency never before possible, creating a panopticon on a planetary scale. The very idea of community would transform. Your neighbors might be beings from a planet orbiting Betelgeuse, challenging our definitions of kinship and culture. What does it mean to be human when humanity is just one species in a vast, interconnected network of intelligent life? This technology could also deepen existing inequalities to an unimaginable degree. If wormhole travel is incredibly energy-intensive, it could become the ultimate luxury, creating a new elite class with access to the entire cosmos while the rest of humanity remains planet-bound. We could see a future where the wealthy literally live in different dimensions, completely divorced from the problems of the world they left behind. The greatest challenge, then, may not be figuring out how to build a wormhole, but deciding who we become once we have that power. The journey through a wormhole is not just a voyage through space, it is a voyage into the deepest questions of our own nature, demanding that we evolve not just technologically, but ethically, developing the wisdom to wield a power that could either unite the cosmos or shatter it. After grappling with the profound ethical questions that wormhole technology would unleash, we arrive at a crucial juncture. Where does the science actually stand today? While a functioning Stargate remains a distant dream, the pursuit of this incredible idea is far from idle speculation. It is actively propelling some of the most innovative and cutting-edge experimental and theoretical work in modern physics, pushing the very boundaries of how we probe the universe's deepest secrets. This is Theory 30, the future of wormhole research, a look at the tangible, exciting steps being taken to turn a fantastical concept into a field of rigorous scientific inquiry. The hunt is happening on three main fronts, each leveraging our most advanced technology. The first battleground is the realm of the incredibly small. To understand how space-time might be woven together at the most fundamental level, we need to peer into the quantum foam, and for that, physicists are turning to massive particle accelerators. While machines like the Large Hadron Collider will never create a macroscopic wormhole, they are our best tools for probing the energy regimes where quantum gravity effects might become noticeable. By smashing particles together at velocities approaching the speed of light, we can recreate, for a fleeting fraction of a second, the conditions that existed just after the Big Bang. The debris from these collisions is meticulously analyzed, with scientists searching for any anomaly, any slight deviation from the predictions of the standard model of particle physics. That could be a signature of extra dimensions or quantum gravitational fluctuations. It's like listening for a faint new note in a familiar symphony. Finding it could provide the first indirect hint that the fabric of reality has a richer, more interconnected structure than we ever imagined. While accelerators probe the microscopic, our most powerful telescopes are scanning the cosmos for macroscopic evidence. The James Webb Space Telescope, with its unparalleled infrared sensitivity, is revolutionizing our ability to study the early universe and the formation of the first galaxies. But it is also an incredible tool for exotic astronomy. By providing exquisitely detailed observations of gravitational lensing events, JWST gives astronomers more data than ever to search for the telltale, anomalous signatures that could betray the presence of a wormhole, a strange double-ringed image of a distant quasar, or a point of light that appears without any visible source, potentially a mouth projecting light from a brilliantly lit region. On the other side of the universe, simultaneously, gravitational wave observatories like LIGO and Virgo are listening to the cosmic symphony of colliding black holes and neutron stars. Researchers are now developing sophisticated algorithms to sift through this data, searching for unusual echoes or persistent hums in the signals that don't match the clean chirp of a black hole merger. A wormhole, with its unique topology and exotic matter throat, would vibrate in a distinctly different way, and catching that vibration would be the first direct evidence that these structures are more than just mathematical ghosts. Perhaps the most mind-bending frontier of all is happening not in deep space, but in the controlled environments of quantum computing labs. In a landmark experiment in 2022, a team of researchers used Google's Sycamore quantum processor to simulate a phenomenon akin to a wormhole. They didn't create a gravitational rift in space-time. Instead, they leveraged the holographic principle. Using a simplified model of a universe governed by quantum mechanics, they were able to demonstrate quantum teleportation, the transfer of information from one point to another, in a way that mimicked the geometric properties of a wormhole traversed by a particle. It was a quantum system that behaved as if it were connected by a wormhole, providing a tangible, albeit tiny, laboratory model to study how gravity and quantum mechanics might be intertwined. This kind of work is revolutionary. It allows us to test the predictions of theories like ER equals EPR in a practical setting, using quantum entanglement as a stand-in for gravitational connection and offering a new window into the mysterious quantum structure of spacetime itself. The path forward is a collaborative marathon, not a sprint. It requires particle physicists, astronomers, and quantum information scientists to work in concert, each providing pieces of a puzzle we are only beginning to assemble. The ultimate goal is not necessarily to build a Stargate next week, but to achieve a more complete theory of quantum gravity, a unified understanding of how the universe works at every scale. The humble wormhole, a concept born from Einstein's equations nearly a century ago, has become a powerful catalyst for this quest. It forces us to ask the biggest questions, to develop the most sensitive instruments, and to imagine the most profound possibilities. Even if a traversable wormhole forever remains out of practical reach, the relentless pursuit of it is already gifting us with a deeper, richer, and more astonishing view of the cosmos we call home. And so, our journey through the cosmos comes to a close, having ventured from the chalk-dusted equations of Einstein and Rosen all the way to the holographic edges of reality itself. We've stood at the mouth of a black hole, peered into the quantum foam, and dared to imagine bridges to other worlds and other times. These 30 theories are more than just a list of fantastical ideas. They represent the human spirit at its most curious, relentlessly pulling at the threads of the universe to see what unravels and what holds firm. While the dream of stepping through a stable wormhole remains just that, a dream for now, this quest has gifted us something arguably more valuable, a deeper, richer, and far more astonishing understanding of the cosmos. The very act of asking "what if" has forced us to confront the deepest paradoxes of physics, driving the development of powerful new tools and theories. Our search for cosmic shortcuts has, ironically, taken us on the longest possible route to knowledge, unveiling the intricate connections between gravity and quantum mechanics, between information and space-time, and between the unimaginably large and the infinitesimally small. These cosmic tunnels challenge everything we think we know about distance, time, and the very nature of reality. They push us to reconsider our place in the universe, not as lonely inhabitants of a single rock orbiting an average star, but as potential citizens of a vast, interconnected multiverse. The pursuit of the wormhole has ignited our collective imagination, fueling both rigorous scientific inquiry and boundless creative storytelling. It reminds us that the universe is far stranger, more complex, and more wonderful than we could ever have conceived. Now, we want to hear from you. Which of these theories captured your imagination the most? Was it the eerie promise of quantum entanglement acting as a physical bridge, the terrifying possibility of a black hole firewall, or the mind-bending idea that our entire reality might be a holographic projection? Do you believe these cosmic shortcuts are woven into the fabric of space, just waiting for us to learn how to see them, or are they beautiful mathematical phantoms that will forever remain out of reach? Let us know your thoughts down in the comments. We love reading your perspectives and ideas. If you enjoyed this deep dive into the heart of space-time, please show your support by hitting that like button and subscribing to the channel for more journeys to the farthest frontiers of science. Until next time, keep looking up and wondering what's